Controversy about an experiment that Professor Lewin has demonstrated a long time ago, and then YouTuber ElectroBOOM had some different interpretation about the experiment, and this caused a lot of discussion on the internet. And I wanted to provide a little bit of clarification, I hope, for this issue. So let's get on with describing what this paradox is. It's not really a paradox, but it's just a demonstration of behavior of changing magnetic fields. So Dr. Lewin set up an experiment where we had a solenoid, basically a long coil of wire, and it had a current through the wire which caused a increasing magnetic field. And he set up two oscilloscopes to measure, and the two oscilloscopes were connected to the exact same point in a loop of wire that surrounded this changing magnetic field. Now, this changing magnetic field had a certain generated a certain potential. Let's just say it was 1 volt, and Dr. Lewin had a 100 ohm resistor on one side and a 900 ohm resistor on the other side, and this changing magnetic field created a potential within the loop, which caused a current. Being 1 volt and being a resistance of 1K, it caused a current of 1 milliamp to flow inside of this cycle. And then the question is, what is the potential difference between this point and this point? And so here we show 2 meters measuring it. 1 meter is placed on the left and the other meter is placed on the right. Both meters are connected to the exact same point in the circuit. And sort of the paradox is that 1 meter reads minus 0.9 volts, which is the same thing as the voltage drop that we would expect across this resistor. And while the other reading meter reads 0.1 volts, which is the voltage we would expect to see across the 100 ohm resistor. So this is a paradox, or basically it's used as a statement that says that KVL, Kirchhoff's voltage law, does not work because the sum over all of the voltages along this loop here is not zero. If it was zero, you would expect both of these meters to read the same value. So the question is why the different readings from the two different meters. And actually, the explanation for this is fairly straightforward, so there's not much controversy in the explanation that Dr. Lewin provided. So the explanation basically works like this. We can talk about different loops. So this loop here that goes across like this loop, since it doesn't contain any changing magnetic field within the loop, then we know there's no induced potential along this loop, and so we have no voltage drop except for the voltage across this resistor, and so we read minus 0.9 volts because these wires don't contribute any additional voltage drop. And if we consider, on the other hand, we could consider a different loop, one that contains the magnetic field, such as this. So now we're going to loop around in this fashion. And what we have in this case is that that because this encloses a changing magnetic field, and the science depends on whether you go clockwise or counterclockwise around it, but if you go consistent with this meter reading, then you're going to have the voltage of this meter reading minus this voltage of this resistor 2 is going to have to be equal to minus 1 volt. And then we can solve that. And that also says that the meter should read minus 0.9 volts. So whether or not we take a path that doesn't include the magnetic field or not, then this meter reading is consistent. And when we look at the meter over on this side, then we find similarly that the loop that's on this side does not include the 1 volt potential, and so we read 0.1 volts. And if we loop over from this side, then we'll have an additional 1 volt, and so the reading will be 1 volt minus 0.9 volts, which is 0.1 volts. So in this respect, everything is explained. It's quite clear how Faraday's law explains the meter readings and why a meter on one side reads different from the other. Now, I would say that this analysis always includes the current carrying part of the loop. In reality, you can see that it's a little bit more ambiguous if we consider this loop that just connects the meters, because we know that this loop, that V1 minus V2 should equal minus 1 volts, or if we go the other way around, you'd see opposite signs. But we don't have any way to say that this one should read 0.9 and this should read 0.1 or anything like that, just that the sum of these should be minus 1 volts. So you could, for example, based on this argument, say we could read minus 0.5 on both. And the reason for this is that in reality, these meters are measuring current, and the current is being shared between this resistor and the resistance of the meter, which is typically some high value like 10 mega ohms. So if you really wanted to analyze, if you wanted to be pedantic about it, you'd have to solve a system of equations to consider how the current was shared between these. But this current that's in this meter path is extremely small, almost vanishingly small. So except for the case that we're including this large outer loop, it's okay to neglect that current at this node. So like, for example, when we take a path that goes this way, we are neglecting the small current that's in this meter path, which would change the results ever so slightly, not to any easily measured degree. But it shows that the analysis of this circuit is actually, there's a lot of simplifications that are made in the analysis and the explanation, obviously. Okay, so no real controversy here. So and it's clear from this explanation that KVL, the Kirchhoff's voltage law, doesn't hold. That the sum over some of the loops is non-zero, which is basically the statement of Kirchhoff's voltage law is that the sums of the potentials along all loops should be zero. Okay, so that's pretty clear. So what's the controversy? Well, the controversy is that ElectroBOOM looked at this and said, I have a different way of explaining the circuit. So what he basically said was that actually it's wrong to say that the meter leads all were at the same potential. They're all forming windings. So like if we look at this meter lead and this part of the this connection and this part of this connection and this part of this connection, that's forming a winding around the solenoid. So it's kind of like a secondary. So instead he said, well, we could treat the meter lead as a quarter of a turn around this loop, and the dots here are indicating the direction. And so now you're saying, well, this end of this lead and this end of this lead are not at the same potential with this argument. And if you go through this argument, then you would say, okay, well, we have a minus 0.25, a plus 0.25, minus 0.9, plus 0.5, minus 0.25. So basically the induced voltages in this segment and this segment cancel, and in this segment and this segment cancel, and that explains why you have the minus 0.9 volt reading. And then if we follow the path around here, all of these 0.25s add together and you get 1 volt, and so that explains it. So it would seem that using these quarter turns, we get the same meter readings, but we have a different explanation for why. And so the main controversy is like which explanation is correct. Now, I would say that when we look at ElectroBOOM, like how do you know this is a quarter turn, you could say. But in reality, actually, that's not an important detail. We could have assigned fractions like this, for example. So we could say, oh, this was just an eighth of a turn, this was 3/8 of a turn, this was 1/8 of a turn. And the only thing that's required to get the correct readings of the meter is that when you sum up the number of turns along any of these loops, that the number of turns that you get is equal to the number of actual turns. So like if we look at this loop, then this would be minus an eighth of a turn plus a 3/8 of a turn minus an eighth of a turn plus 3/8 of a turn, and so it's going to be 0 turns. Likewise, if we take the loop from here around here, you're going to have 1 turn. And so from that perspective, you could say, well, all we're doing here is we're just adding some potentials to the loop, which ultimately, when we solve the system of equations, we could move those terms over to the right-hand side, and it would be mathematically identical to the way we would solve the problem if we were applying Faraday's law exactly. So from a pragmatic point of view, actually, these fractional windings don't matter. The only thing that matters is that the sum for any loop actually equals the actual number of windings. And once that's set, then you will obtain the exact same results as an analysis that said that Kirchhoff's voltage law didn't hold, but we had to add these loop potentials to each loop in the circuit. Okay, so there are 2 different ways, it seems, of stating the same point. Now, I think that the real question that we get into here is there something wrong with ElectroBOOM's explanation? So it does explain the meter readings by introducing an induced EMF in all of the wires. Now, some things that this brings up is, there are changing magnetic fields in many circuit components. And so, why are we concerned about these induced EMFs in every wire? Generally, we just consider induced EMFs in the wires of transformers and motors and so forth. So why most of the time can we ignore these induced EMFs? Also, a question would be, why is the assignment of the induced EMF to wires non-unique? As I said, we can use ElectroBOOM's method, and actually how we assign how much of a fractional part of the EMF is assigned to each wire segments is not specific. We do have to satisfy certain properties, but since it's not specific, maybe it's not really physical. It's just a artifact of how we add, or we're basically contriving a way to make the circuit satisfy KVL. And actually, that's maybe a perfectly reasonable view, and it's actually sort of the pragmatic view that I take to this. But I think there is more to it than that. Sort of tied into this is the question of how do we verify what is a lumped model of the circuit? How do we relate the lumped model to things that are actually happening in the PDE? And sort of a sub-question is like, is it really possible to create a lumped model of Lewin's circuit? It would seem that the approach that's proposed by ElectroBOOM predicts meter readings, so that would seem to suggest that maybe it works, but how do we validate that approach? I would say that you would validate that by just showing that the assignment of the fractional turns and the EMFs leads to the same set of system equations as if you said each loop has its own potentially non-zero potential. But it would be more comforting if we knew there was like a single fractional turn assignment that was more correct, because then that would say, okay, that's actually tied to physically what's happening. So the explanations, the meter readings by these 2 proponents are different. Lewin's explanation is obviously a correct application of the physics, but does this make ElectroBOOM's explanation wrong? And if so, why is it wrong? So I want to kind of dig into this a little further. So I want to actually interrogate the solution of the partial differential equations in the context of Lewin's circuit and try to understand what is represented by a lump parameter model, for example, like ElectroBOOM is constructing. Okay, so let's just talk a little bit about these lumped models, or what's often called lumped matter discipline. This can actually occur in many different disciplines, in fluid mechanics but in electrical engineering models. Lump matter disciplines are one in which basically the general principle behind lump matter disciplines is that instead of dealing directly with partial differential equations, we do some integrations of the partial differential equations in some controlled way. And these integrated variables reduce the partial differential equation to a set of ordinary differential equations. So this is traditionally done in electrical engineering, and the approach that's done requires, or I wouldn't say requires, but the basis upon which lumping is usually described requires the following conditions are held. So one of them is that there's between the conductors, or if you look at conductors that connect various components in the circuit, that the loops that they define, that there are no changing magnetic fields that loop cuts. Okay, so this actually facilitates Kirchhoff voltage law. Also, the assumption is that the charge density inside of the conductors doesn't change in time. So this facilitates Kirchhoff's current law. Also, another thing which is kind of related is that the time scales of interest is much longer than the time it takes for electromagnetic wave propagation. So normally, if it takes a certain amount of time for light to propagate across the geometry of our circuit, you might need to have at least 10 times that amount before conditions that we described above actually hold, because it takes time for this information about how charges are distributed and so forth to distribute. So these are the general conditions that are required for a lumped model to hold. This is basically the question about ElectroBOOM's explanation, since in the circuit clearly this first constraint is not being held. Now, I would argue that it's not, that these are necessary conditions for, and when these conditions are being held, that you can that you have a specific interpretation of how the integrations are performed. But I would say that there can be other ways of defining integration, and as long as you are consistent in how you define those integrations, then you can create a lumped matter discipline that doesn't necessarily satisfy these conditions. But obviously you need to be careful, because now you're doing something that's kind of outside of the basic definition of how the lumped model, how the parameters in the lump model, what they mean, how they connect to the actual partial differential equations. Okay, so now I'm going to do some computational solutions to these field equations. So first I would like to describe a little bit about how this works. So the first thing I'm going to talk about is just modeling electrostatic problems using an electric potential equation. And so in this case, we would consider that the electric fields are conservative fields. So conservative fields are fields which can be defined by the gradient of potential function. So a simple example of potential functions would be a gravitational potential. So like if we have some surface that has hills and valleys, the height of the surface can be considered as related to the gravitational potential function. And if you take the gradient of that height field, you have an idea, you have how much force that field will impose on something. So if you put a ball on this surface that's varying in height, it's going to be forced to move in the direction of the steepest descent. In other words, in the gradient of that height field. In a similar case in electric fields, we have a potential field, often called the electrostatic potential. And in that sense, the forces that the electric field endows is given by the gradient of the potential function as indicated here. The electric field is the negative of the gradient of the potential, which here I just give it the variable V for voltage. So now that potential function, you can find the electrostatic potential. It can be inferred from the distribution of charge throughout the volume by solving this Poisson equation. So this is the Laplace operator, involves second partial derivatives of the potential function. And when we set this Laplace equal to the Laplace operator of the potential equals to the negative of the volumetric charge distribution, when we solve this equation, we will obtain the potential function that those charges produce. And this is just instantaneously true. It doesn't evolve in time in this form. We're assuming enough time has occurred that all of the information about the instantaneous location of the charges have propagated. Now, in conductors, charges are allowed to migrate, and the current induced by the electric field is, which we, as a vector field, we'll call J, capital J, and that is just related in a simple conductor by a conductivity coefficient. So we'll just multiply the conductivity coefficient times the electric field to determine the current. So if the conductivity is larger, you have more current in response to an electric field. Now, once we have this, we can actually solve an equation for how the charge within a conductor evolves in time. So what we do is we just say, okay, the change in charge as a function of time plus the divergence of the current is equal to 0. This is kind of like a KVL term. So basically, if there's more current that's going out of a region of space than is coming in, then the charge is going to go down, and vice versa, the charge is going to go up. And we can express this directly as the evolution of charge is divergence of sigma times E, because this is just a restatement of the current. Okay? So this gives us a way of solving how charges would move in conductors and so forth in electrostatic problems. No changing magnetic fields, no moving charges. So this is electrostatic. Now, when charges are moving, the electric field is no longer conservative. That's because in addition to the electrostatic potential, this potential due to the instantaneous location of charges, there's also what is known as a magnetic vector potential. So this vector potential, often denoted by the variable A, is a vector field, and it's defined such that the magnetic field is the curl of this field. And with a little bit of work, you can actually show that you can derive a conservative field from the electric field. We'll call it F, and where we take into account the effects of the magnetic vector potential. And this F field we can again solve with, or we can again find by just finding the gradient of the what's called the scalar potential. The scalar potential is the potential that's caused by the instantaneous location of the charges. Now, once we've defined this vector potential A, we can then define the electric field, again by kind of feeding back into this, as a correction on the electrostatic potential field. So we now can define the electric field as the negative of the gradient of the potential field minus the change over time of the scalar of the vector potential. Okay, so now in the Lewin case, we're considering a case where the solenoid has a magnetic field that's increasing linearly over the small interval of time that we're doing this analysis. So this partial A, partial T, and if we neglect the self-inductance of the winding that's outside the solenoid and so forth, then we can basically impose this vector field as just a constant function. It's being generated by the solenoid. Now, what does this potential field look like? Well, if we assume that magnetic field is of uniform concentration over a cylindrical area, then actually using Faraday's law, we can actually determine that the intensity outside of this cylinder, that the intensity of the electric field would decay with the reciprocal of distance. And so with a little bit of work, I won't go into all the details, but you can actually show that the magnitude of this vector potential increases proportional to r until you get to the outer end of this radius, and then afterwards it decreases with the reciprocal of distance. For this specific case of a infinitely long cylinder, this makes it fairly simple to consider this problem. And so now we have sort of how we define the magnitude of the potential field, and similarly you can show that the potential field is going to circulate around this magnetic field. It's going to be diminishing, and it's always going to basically be tangent to circles that are centered on that cylinder. So this function is relatively easy to define, and this gives you enough information that you can actually define the A field. It's an increasing function of t, but because the magnetic field is increasing linearly, then this just becomes the partial A, partial t just becomes a constant function, a constant field that's distributed in space. And so we'll just impose that in our simulations. So let's just summarize what our model is going to be. We're going to have a scalar potential equation, which is defined in this way. By the way, we're using this Q bar to indicate we're using a non-dimensional value. We're shuffling some of those constants under the rug. We have a charge flow equation, which allows the evolution of charge in time. And this involves the current. Here we're using a non-dimensionalized version of conduction. We're not really interested in the exact value of the conductivity. We just want to know the relative amount of conductivity. So like if we have a resistor, one resistor is 10 times larger than the other, then we make the conductivity 1 over 10 and 1 over 100, then we have a factor of 10 between them. What we're going to do is we're going to just converge this such that del Q del T is equal to 0, and then we'll have sort of the static solution. But there is kind of a question, how long is enough to reach these conditions, and where do they need to really be held? So we'll talk about that a little bit more later. We define the electric field using as a function of both V and A. V is going to be a function of the instantaneous distribution of charges, and A is just a constant function that's imposed. And we're going to impose this vector potential, where we're going to set it up so that one winding around the solenoid would produce a 1 volt potential. This model is assumed to be 2D with infinite extent in the z direction. Also at some distance, let's say infinity, but it's actually just like 100 times farther away, we're going to just set the potential to 0 so that we anchor the function and it's well posed. Also, initially, we're just going to assign the charge to 0 everywhere. Okay, so these are uncharged conductors, and we're going to then just let the charges flow around in response to the electric fields and see what things look like. I do want to mention a little bit about the effect on potential difference when we start considering magnetic fields. So in the electrostatic case, we can define a potential difference as just the difference in the scalar potential. However, when we have moving electric fields, then that's going to be different than the integral of the electric field between 2 points. Now, the integral of the electric field is more related to actually work. So like the electric field is like a force, and if we moved a charge through that path. So in some ways you could say that this is a more physically meaningful way of talking about potential difference than this one when we have magnetic fields. However, because the electric fields are non-conservative, then the path that you take is going to change what your potential difference is. So this is one complication here, because actually it turns out that in the traditional way in which the lump discipline model is developed, the integral, it's defined in terms of the integrations of the electric field when we talk about potential differences between nodes in the circuit. So a lot of the arguments about these different explanations are really arguments about what definitions you're using or what is the meaning of the voltages that we compute in the lumped model. So here, let's just show how I'm going to set up this numerical simulation for the Lewin experiment. So here, where there's not a conductor, it's black. There's just 0 conductivity. And then we have just a conductivity of 1 is given to what we would consider a good conductor. And here we're implementing resistors by having a reduced conductivity, not 0. But we want to make this small enough that that most of the effective resistance is actually found in these 2 resistive sections. So on this section, we're going to have 1 over 900, 9,000, and this is going to be 1 over 1,000. So that means that these will have a resistivity that is 1,000 times or more greater than the conductive parts. So about 10 degrees of the loop is 1 over 9,000. So this is kind of representing the 900 ohm. And about 1 over 1,000, about 10 degrees of the loop is this 1 over 100. So that's going to be similar to the 100 ohm. So we're really just concerned about the ratio there's between these two. So one that has a resistance of 9 times the other. So when we have a 1 volt potential that's induced in this loop, we would expect to see about 0.9 volts dropped across this resistor and about 0.1 volts. So that 1 volt's dropped across that resistor. Okay, so let's see what the electric field, or first of all, let's talk about the solenoidal, the vector field that we're imposing. We're going to be placing the solenoid in the center of this conductive loop. And so this is just a plot of the scalar potential to give you an idea of exactly what that solenoid is doing to the electric field. It's imposing this circulating electric field. And if we go to the next part, we can see this is actually what the simulated electric fields are once we've run this until the currents have equilibrated. And some of the things that we notice here is that there is no electric field, or essentially 0. There is a small one. There's very little electric field within the conductors, and There is a very large electric field on the higher resistance section, and the lower resistance section has a somewhat smaller electric field. We can also see the circulating electric field lines here, which is an indication that there is a magnetic field present, because you're not going to have these closed circular lines that don't connect with any solid surfaces unless we have a magnetic field. Okay, so this looks actually a lot like the sort of the explanation that we have of Lewin circuit, with a large potential on the left and a smaller potential on the right. Not really much electric field or potential difference within these conductors. Okay. Now, we can also look at the charge distribution within the conductors, and what we can see is that the charges have migrated to the surfaces to where there's discontinuities in conductivity, both to the edge where the conductivity went from 1 to 0, but also at the edges where the conductivity went from very conductive to less conductive. We can see that within the conductors we had charge separation. So one side of this conductor became more rich in positive charges, and the other side became more rich in negative charges. So I guess, one of the things that we can ask is what explains this separation of charges in the conductor surface? One of the things I'd also mention is this charge density. It's a volumetric density, and so the actual magnitude of it just depends on how fine of a mesh that I used for the conductor. If the mesh was finer, the density would have been even higher. Physically, that will be very thin. It won't be vanishingly thin, obviously, because the charges are carried by atoms and electrons floating around between them. In reality, that's going to be dictated by solid state physics. It's going to be dictated by thermal interactions of the electrons with the atoms and so forth, but that's a detail that goes well beyond what this model is covering. If we look at the scalar potential, what we see is that there is, in the potential field, we can see that on this side here, this end of the conductor is about minus 0.45 volts, and on this side here it's about 0.45 volts. So it confirms that there is, in the scalar potential field, there is about a minus 0.9 volts if we're reading, if we put the meter with the positive lead here and negative lead here, there's some minus 0.9 volts across that. Similarly on this side, it's about 0.05 to minus 0.05, so there's about a 0.1 volt drop across this resistor. But the other thing we do notice in the scalar potential is that there is a continuous change in the scalar potential along these conductors. Okay, so while when we look at the electric field, we see that the electric field is 0 within the conductors. In the scalar potential field, in other words, in the charge distribution on the surface of the conductors, there is a continuous change that happens through the conductor. Now, I also want to look at a kind of a related question. What happens if we move the changing magnetic field outside of the loop? So in the Lewin paradox, the 2 meters have different readings because of that magnetic field. And so if we move it outside, then the loop should not have any induced current, and there should be we should be able to see that the electric fields within the conductor is 0. So that's what the consequence of having no induced currents. And what we should ask, what does this look like? What is the state of charge distributed in the ring? What is the scalar potential? What does the current look like? So we're going to repeat the same simulation, but we'll move the solenoid to the right of the loop and see what happens. Okay, so here's what we're going to do as our simulation. We're going to move the model over, or the definition of our um, a partial A, partial T source term. We're going to move it over here to the right. And so let's see what our simulation produces. Well, it's not too surprising. Because this is of infinite extent, it actually acts as a Faraday cage. And it doesn't really matter that there were some resistors in here. Eventually, the current is going to distribute in this cage such that the electric field will be canceled within the conductor, and once the electric field is canceled within the conductor, it's going to be canceled everywhere inside of the cage. Okay, so and if we look at the charges, what we can see is that the charges are just on the outer surface of this conductive ring, but we can also see there was a net charge migration. So the top part of this ring became more positive and the bottom half became more negative. So we might ask a question, how did that redistribution of charge occur? We can look at the scalar potential, and what we can see, if we look at the scalar potential, there was positive charges up here, and so it's not a surprise to see that actually this is at a higher potential than this. And so this does show that even if you don't enclose a magnetic field, it doesn't mean that you're not going to have some effect on the distribution of charges within the conductor. That's what we see. Now, there is something interesting about this simulation. This simulation took much longer to converge than the first simulation. And so there's a question, why did it take longer? So I think this is an interesting question, so let's just look at it. So I'm going to show some animations of the simulation evolution. And the simulation where we start is going to be at 1,000 time steps, and at this point the conductor's electric field within the conductor part was essentially zero, so by implication our del Q del T is zero inside the conductors. So that implies that the Kirchhoff current law is holding. So it seems like a lot of this relaxation is actually happening under a context where actually the lumped matter discipline should apply. This is a loop that's outside of the magnetic field, and so we can maybe understand this in the context of a lumped matter discipline, but we'll see. So let's just have a look at what these transients look like. So if we look at the electric potential, what we can see is that at the beginning, there is a potential drop across these resistors. And that potential drop is the result of current flowing from the bottom to the top. Okay, so because we had to redistribute the charge, just as I had shown before, we have negative charge on the bottom, positive charge on the top, so we had to have some way for that charge to get from one side to the other, and it's going to have to go through regions that have less conductivity. And so, that's what we see. In the electric field, we also see initially there's a lot of electric field in the center, and that this slowly decays away. Okay, so now the question is, what's dictating how long this takes? How could we maybe come up with an estimate of that, maybe even before we ran the simulation, so we could know how long we would need to run it? Well, I think that we can probably figure out what's controlling this. So let me propose a lumped model for what's going on. So I'm going to say that this is actually related to an RC constant. So what I'm going to say is that we have a lumped model that looks like this. We have the solenoid, which is the primary winding of a transformer, and we have a parasitic winding of this transformer. And this parasitic winding of the transformer is coupled through a parasitic capacitor to the loop. So the loop here is these two resistors that are connected together. But in addition to this parasitic coupling to a parasitic winding of the solenoid, we also have a parasitic capacitance which comes between the inner parts of the conductor of the loop. So we have basically two parasitic capacitances, and when we start the simulation, it's as if the solenoid had instantaneously, well, first of all, when we started the simulation, the Q was set 0 everywhere, so the capacitors are discharged. But instantaneously, there's a potential across this loop because instantaneously the magnetic field started increasing. This instantaneous potential, these capacitors charged immetimately through one another. The resistors didn't play a role at that very first stage. And then the capacitors were then equilibrated or discharged and or charged through these resistors. And the controlling time constant is going to be related to the value of these capacitances and the value of these resistances. And that RC time constant would give you some estimation of how long you would need to run the simulation. So let's look and see if this, now we'll look back at the animation of the electric field and see if we can make something of this model. So here's what I'm basically saying. I'm saying that these electric fields go around the solenoid and connect back to the outer part of this. And you can see this is a charged capacitor. There's positive charge here, negative charge here. So it looks like a charged capacitor. Similarly, we see that there's a charge distribution on the inner surfaces of these conductors, and that represents a capacitance between these electric field lines represent this capacitance, a parasitic capacitance between these two sides. This, by the way, is a snapshot at that 1,000 time steps. We see these two resistors on either side. There's current flowing through them. On both of them, there's current flowing up, and so we're seeing electric field lines that are going through these resistors as this current flows. Now let's have a look at the animation and let's see if we can get an understanding. What we can see is that most of these field lines on the outside don't really change in time. That's because that capacitor was mostly charged in that initial transient impulse. And that's also what set up the electric fields inside. In fact, what really happened at the very first moment is charge inside this conductor. Some of the charge moved out from this side to the other side. So essentially what was happening when it did that is it was charging this capacitor through this capacitor. Then after that, what we can see is this charge, see this is largely negative, this is positive. These charges are flowing through the resistors, discharging this capacitor. Okay, so this explains what we see in the simulation. And I suspect that you see the connection to the lumped model. You see things in the simulation that you didn't see the first time that I showed it to you. So, this lumped model actually gave us some power to interpret what was going on. So, does the lump model that I provided explain why the simulation took so long to reach equilibrium? I think it does. Does the model have explanatory power? Yes, I think it gives a lot more insight than just the Maxwell's equations does. It adds to the understanding of your simulation results. There's things that I noticed in the simulation right away. Once I had developed the lumped model, I noted things about the simulation. I could provide meaning to it that I didn't observe before. If the presented lump model is valid, then why does adding this induced potential for the electric field coupling to the solenoid, work? If it's valid, why does it work? And if it's invalid, what prediction does it make that's inconsistent with the simulation? If a lump model of parasitic effects here work, then why don't they work in ElectroBOOM's model? It's very similar, but I think we can dig into this a little bit further. Okay, so some comments on the lumped models. I think the main protest against the fractional turn solution presented by ElectroBOOM is that this resulting lumped model no longer satisfies the conditions that the potential differences across the components are defined by the integral of the electric field between the connections or pins of the components. I note that this doesn't mean that the path follows the conductor. If we have a magnetic component, actually we can define the potential difference by just choosing a path that goes across the windings, so we don't have to follow the conductor. In fact, that's typically how we define the integration for the lumped model of things like inductors and transformers. But I would also argue that there are many cases where we use lumped models where at least some of the potential differences of nodes in the circuit are actually not something that you could integrate an electric field to obtain. Okay, so I'll just cover one such example. So consider we have a transformer modeling a load. So we have a model for the transformer, ideal transformer, and you could say, okay, all the magnetic field is contained within the transformer. So when we want to know the potential difference between these two terminals of the transformer, instead of integrating the wire through the inside of the transformer, which would then bring the magnetic field into this loop of the circuit, what we can do is integrate along this path here. And as long as this path is outside of the changing magnetic field, so that this loop here is outside of the changing magnetic field, then we can define the potential difference between this point and this point in terms of the integration of that electric field. Similarly, we can do that here. Okay, that all sounds great. But let's consider the case that this transformer has a winding resistance. That resistance is distributed throughout this transformer. So what do we typically do in a lumped model in this case? What we typically do is we add a resistor in series with that winding. Okay, what's the consequence of doing that? Well, the consequence of doing that is that the potential difference between nodes 2 and 0 can no longer be defined simply as an integral along some path of electric field in the physical circuit. So this lumped model is not strictly satisfying that potential difference. But there should be no question that the integral of the electric field between the terminals of the transformer would match the potential that we obtain between 1 and 0. So this is just like an intermediate node. It's where we're basically using the circuit to do some algebra for us. In this sense, it's not necessarily, it doesn't make a lumped model invalid just because some of the terms in it do not define potential differences according to this standard way. So I would say that the model that ElectroBOOM used to explain the meter readings is not wrong. You can explain the meter readings by saying there's an induced EMF in the meter leads. However, it is potentially dangerous, and it's dangerous because of we normally compose circuits. So we have a circuit and we start adding other elements to the circuit. And when we add those other elements to the circuit, we're not expecting that we need to add these EMFs. It may not be obvious that we're adding a loop that goes around the magnetic field. So anytime that whenever you did something like this, anytime that you look at the circuit, anytime you make any change, you're going to need to re-verify that the sums of the induced potential is consistent with the actual turns that loop makes. So this is tricky if care is not taken. It doesn't make it invalid, but it does mean that you need to be careful when using this induced EMF way of explaining what the circuit is doing. Now, I would say to prove a model is incorrect, you have to be careful of how you make your argument. What I see often done is an argument on one side that says, see, my explanation is different from your explanation. Therefore, since my explanation is correct, your explanation must be wrong. However, it's very common in physics that we have multiple different explanations for the same phenomena. The way that you show an explanation is wrong is not to show that it's different from a right explanation, but rather to show that predictions that it makes are different from actual measurements. Showing that the meter reading is 0 along the conductor does not prove that the induced potential explanation is wrong. Indeed, this explanation is consistent with an explanation that we'd give if we were looking at the scalar potential field. It's just a different explanation. So for example, let's just consider ElectroBOOM's explanation of the 0-volt reading. What he would say is that the meter's probe leads were partial windings, and because they were partial windings, the sums of all of these windings would be contravariant. So you would actually have these windings here would cancel any induced voltage that was in this reading, in this part of the winding. So that's why the reading would be 0. It works. There are things that you could, valid criticisms you could make, or that it's dangerous and so forth, as I mentioned before, but I would say it's not wrong. And I would like to just do a simulation of this so we could see what physically it's actually telling us. So here's a simulation I have created. I have a loop of wire around the solenoid. We can see this high potential that's created in this gap. But I'm going to add this probes for a meter. So I'm taking these probes, bringing them around like so. And we can see here where the meter is. It would have a 0 reading. Now, the explanation you would have for, from Faraday's law is that this loop does not enclose a magnetic field, and so that's why this potential is 0, whereas this loop here encloses the magnetic field, so that's why this potential is present. Okay, that's fine. But when we look at the charges, we see, although we're saying that this is all at the same potential, we're seeing that charges are distributed in a very kind of uniformly increasing way as we go around the loop. So it's not the whole picture. When we look at the potential, what we can see is that the potential, when we go back to the probe, it's not uniform along this whole path. In fact, if we just look at the potential of the conductors, if we just look at the scalar potential, the argument looks exactly like ElectroBOOM's. Okay, so it seems to me that it is related to this EMF explanation of the meter reading is related to things that are physically happening in the experiment. It doesn't contradict the measurement of the 0-volt reading, so this is all perfectly consistent. So in conclusion, both explanations are valid. From a pragmatic point of view, you could just say adding these induced voltages as fractional windings is no different from applying Faraday's law. If I want to validate that I'm doing this correctly, all I need to do is validate that the sum of the fractional terms matches the actual terms in the circuit. Some of those terms are going to cancel. Some of those terms will be actual terms. In the end, they always need to be some integer value. If they're not, and consistent with the circuit. If they are, then mathematically, when you solve that system of equations, that's going to be the exact same system of equations as if you said each loop has its own potential and you listed them out. It's the same thing. There are some advantages to the approach in terms of accounting for energy transfer to the magnetic field and so forth, in my view, and the fact that we have lots of tools for simulating circuits. And we also have a lot of intuitions that are based on KVL. So there are some advantages to using the induced EMF view as well. A wire that has an induced EMF across it will have a different scalar potential across it. The EMF does not relate to something that occurs, that is something that relates to something that physically occurs in conductors, even ones that don't form a loop that enclose the magnetic field. Using the EMF as an explanation, it needs to be used with care. Once it's utilized, then the induced EMFs potentially need to be considered for every conductor within the circuit. But it is a valid explanation of the meter reading. So as far as I'm concerned, both explanations are valid. And the level of controversy is not helpful. I think it's more useful, actually would be much more useful to have conversations about what you need to be careful for if you're using induced EMF rather than just saying this is wrong. The reality is, like many models, talking about induced EMFs is useful fundamentally, and in many contexts that alone is a good reason for them. But there's also some good reasons to use some caution when using induced EMF. So if you don't know exactly what you're doing with the lumped model, if you're not exactly clear of the consequences, you should probably use caution. But the models are both valid ways of explaining what has occurred.